All right. So let's start the course. Please write me in chat if you have some video or sound problems, or if you cannot see the screen, so I will try to immediately react and fix it. My name is Alexander Pachenko. I'm assistant professor here in Skoltech, and my field of research, my field of interest is natural language processing. And today I will start in a course of statistical natural language processing, and basically an introductory course on NLP here in Skoltech. All right. Today we will first speak about the course itself, some logistics and its goals. Then there will be some short introduction about main concepts of natural language processing. So we'll speak about what it is as a field, what kind of tasks we usually deal with. And then we will speak about some basic approaches, which actually is useful still in some cases, which let you directly jump into solving some simple NLP problems, which are mostly based on rule-based approaches. And as one of the exemplar of these approaches, we will speak about morphology. And how to solve morphological analysis with such tools as inferences transducers and various search trees and other structures. Then our discussion also will be finished with some basically some further directions on morphology and more future work and more recent works, but only as kind of highlights. All right, so this course is will rely on several sources. There is a course by Chris Beeman, so I was working before also with Chris, and at least some of the lecture today is based on a course designed by Chris. Also, we will be basically based on somehow classical already textbook by Daniel Churavsky of Stanford, and also Martin from U Colorado. This book also supported by the course of Daniel in Stanford. But there will be also some other parts from other sources, and actually we will have a guest lecturer, hopefully from Yandex, Dmitry Yustalov, who will speak about some graph-based topics, and also about crowdsourcing for NLP. So basically trying to collect the data for your applications as he works in Yandex Tolaka team. All right, so the course, yes, as I mentioned, it's based largely on this textbook, which is now the third edition and still in preparation. And the nice thing about this book, you just have all available books, chapters, which are currently written online. And also, you can refer to earlier books, which also described basic methods and statistical approaches to natural language processing. Basically, pretty much the first book which changed the landscape of teaching NLP was the book of Marin and Schutze, and like in 1999, 2000. Before this, pretty much all the NLP was based on the rules, and the main paradigm was based on the rules. And this book popularized largely this idea of using statistics and processing languages lately. All right. By the way, because the course is interactive, I really encourage you to ask some questions or to stop me, or if something is not clear, to give some feedback, because yeah, it's not so fun just to sit for 3 hours beside my slides with no feedback. And yeah, I hope that's not forever. Okay, so the goals of this class is basically to you to give some initial introduction into the field of natural language processing, and get some idea about what kind of things we do usually when we do NLP, what kind of algorithms and technologies are used to build some various projects, and also if you fall in love with this field, with this kind of domain, it's a nice opportunity then to learn about it and maybe to select it for your future work, future research within the Scholarly Master Program, or yeah, maybe eventually even apply for PhD in this field. Here's just a few small examples of master or student projects which has been completed before in the group in Germany where I worked, or some of them were done here already in Skaltech. So this is a application called the Network of the Day and Tages Network, and basically what it does, it gathers everyday streams of news articles from various sources. It's basically just a bunch of RSS collections, and then what happening is name entities such as Audi, Volkswagen, Daimler, and names of persons are extracted, names of political parties, and then on the basis of some co-occurrences of these entities and maybe some verbs, what you can observe is like a visualization of today's agenda, what happened on the news in the form of a graphical network where you can navigate and then see, okay, which entities co-occurred and appeared with this in which events. And this is just an example of some kind of a fancy application, which is not very hard to develop, but might be useful for some cases. Here is another idea of NLP application which has been developed by a master student back in Hamburg. Actually, his master's thesis got converted even in a paper at the CGI conference a couple of years ago, like you. And the idea of the system is that what you want to solve, you want to help people answer comparative questions, such as whether Python is a better language than MATLAB for, let's say, writing some deep learning programs. And the way to do it was to gather a really large text corpus based on common crawl. So this which performs the dumps of the web every month, I think, like reasonable dumpling dumps. So basically, what you have a very large corpus, like think of Yandex scale, but maybe 10 or 20 times smaller, and then to build a really large index, and then to retrieve sentences where both objects appear, and then you basically classify them with respect to the polarity, like whether this sentence characterizes the fact that Python is better than MATLAB or vice versa, and then it gets to this or this column, and we actually crowdsourced a data set which basically has its annotation, and because for this task, obviously there was no special data set, and this is why we want to teach you how to solve the tasks of creation. If you have some task in mind you want to solve, chances are, if it's innovative, there will be no data to train. And then this kind of system would count how many various statistics on the sentences and show and extract some aspects based on actually simple rules, such as those we will learn today. Actually, what you can have, you have something a little bit better than Google in terms of 10 rulings, like a kind of visualization of this system, and you can even have an online demo available on this system. And another system which also was developed actually by like a German master student, Fide, and this work also got accepted at some demo session at NLP 17 conference in Copenhagen. So this system would disambiguate words in context. So let's say jaguar can be like a predator, like animal, or it can be a brand of some expensive car brand. And basically what he developed, he did an algorithm which would perform this disambiguation in context. And also the nice feature about his system was that all of these nice visualizations of senses and these tags, and all of this was extracted completely automatically from text. So he didn't use any dictionaries or something like this. And the system is actually available online. So the idea that you can type a sentence and then kind of annotate what we can sometimes semantify text using these images labels, which would, for instance, help you to read easily better this text. Yeah, so that was another example, and the most recent one is also along these lines, along the word sense, what we call word sense disambiguation thing. This is when you have a word in a context, you need to disambiguate it depending on different senses. And and then the feature of this latest system, which was also published in recent conference, like virtual conference. Unfortunately, it was supposed to be in France, but yeah, it was virtual. is that we done this word sentence distribution thing for 158 languages without using any resources except a bunch of pre-trained word embeddings. So really the nice feature of this approach, this system, was that the only thing you just need this bunch of word embeddings, and then you have this interface where you throw in some text, like in any of these languages, the language is detected automatically, and then the words in the language got disaggregated. Yeah, then you don't need some annotated data, you don't need anything, you can get some level of quality with the system. And also the system induced some sensors for each of these languages. So these are kind of, yes, technology which was used. So this is why we speak about a graph-based approaches in this course. So basically what is behind is some graph-based clustering of the ego network of the words. Let's say you have a word Ruby, and then you have a bunch of words which are similar. So what you do, you draw that kind of network, and then you try to segment so to find groups of words which are tightly connected, and they usually would correspond to word senses. It's like on Facebook, you have yourself, and then you're surrounded by people from Skoltech, or maybe from the first university you graduated from, or your friends from your secondary school. They kind of group together, but they do not. They only linked through you. They're not connected to one another. The same can be done for if you draw a network of words and then try to segment it. Yeah, so these are kind of applications which we work on, and yeah, if you after completion of this course you like it and you want to do something like this, yeah, that might be one of the options. Don't contact me. All right. Logistically, we will also run the course like this. We are given a slot of 3 hours for the lecture and for the seminar. We will have a couple of breaks during this 3-hour slot. I think neither you, neither me can focus for such a long period without a problem. So I think we will have something like 45-minute session, and then something like 10-minute, maybe 15-minute break, and another 45-minute session, some 10-15-minute break. There will be 2 such breaks during the lecture. Okay. Yeah. What is inside the course? So first component is to try to give you some ideas about the algorithms and basic algorithms which are used to do NLP. And second component is also important, that to show you actually where these approaches can be used, which kind of data they can be applied to. We try to give you on the seminars some hands-on experience with writing and guiding you through how to write different parts of things in Python using Colab environment. So this goal of these seminars is to prepare you to the homeworks. By the way, in the canvas, the separation between for the scores between is not correct. I will speak about the correct separation and fix after the lecture the grading criteria. So the main idea is that I try to give you the lecture so that you understand, get some basic concepts about NLP, about what you can do, how you can do it. On the seminars, you try to get some more concrete hands-on experience to interact with these concepts. But ultimately, what will matter the most is you doing some of these things yourself during the homeworks, 2 homeworks, and 1 final project. Homeworks are individual, final projects is group task. So this is basically the schedule. It looks like this. So we are here today at the first session, the first topic. And then we will have 2 lectures, 2 seminars before the first assignment. Then the first assignment is like 2 weeks, spanning from 16 to 20 of November. And then will be another assignment, and then you basically have the deadline for the final project. And there is no exam because we run this course online, and I pretty much don't see the point and technical possibility to do any exam in this setting. So important is to understand that we will specifically reserve even a couple of seminars for discussion, distribution and discussion final topics for the final projects. And then so that we can provide you enough feedback and you know what to do. Okay. If you have any questions, feel free to ask us something.
What is your grading criteria? I missed it.
Yeah, it will come in a second. Yeah, It's exactly the next slide.
Okay.
Yeah. Thank you for the question. So, as I mentioned, there will be no exam, and there will be 2 assignments and 1 final project. For the final project is a group of up to 5 persons, and the assignments are individual, and they are worth each 30%. For the assignments, you will be given tasks, and you will be given online platform based on Codalab. Do not confuse it with Colab. It's a platform to like Kaggle, like you can upload your solution, and then you have kind of a leaderboard, and you see what is your performance on the test set, which is a private and you cannot access it. And you will be also given for each of the tasks some kind of a baseline, but the better you do with respect to this baseline, the better score you get. Of course, it's not the only criteria. We actually even decided to set this now to 5 to 5. So yeah, if you are in the top 20 about leaderboard, you get extra 5 scores, not 7, that to be fixed. But okay, if you improved our baseline, it's also 5 scores. So results matter. But what also matters is readability, reproducibility of your code in terms of a Google Colab sheet. So you submit it, and TA or me, we take a look for it. We try to execute it, and if nothing works or it's like super messy, well, that's not good. if we can step by step get the code, maybe with some minor problems. That's fine. Also, what would matter is your technical report, how it's written, what did you do? So we want just to understand not only from the code, because it might be really hard, what did you do, but from some text description. And we want to get a gist of your results, like comparison to the baseline, whether your approach performed worse or better doesn't really matter. What matters is that you are able to describe it. The final, the similar structure, but a little bit more elaborated in terms of preparation is for the final project. And the difference is that you also have some related work which is not relevant for assignments because the tasks are fixed. You not really selecting the task yourself. Here you do select it, and you do select the method yourself of really. And also what will be another deliverable for the final project is a kind of a pre-recorded presentation where you don't only submit a technical report, we also submit some kind of presentation presenting this technical report paper. And what actually this exercise does, it models a real research work in the field of NLP, because if you want to write a master thesis or PhD thesis or do some research project in NLP, well, there will be pretty much the same criteria. People will judge you and judge your project. So they will look at what did you do, how well your solution performs with respect to some other approaches. They will hammer for the reproducibility of your code, because if you just say, oh, I developed the best algorithm out there, but yeah, I've lost the code, but anyways, I got numbers, that doesn't work anymore. Maybe it did work 10 years ago, but really today it's just a de facto standard that you gotta reproduce and show the code. And of course, then you've done something nice, you want to write it up and submit to some conference so that other people can understand what it is. And this is where you will practice it a bit. All right. Do anybody have any question about this part?
Yes, I have a question, Professor. Can you please return to the previous part? I didn't get one thing. The previous slide, please. You written like assignment 1, assignment 1, assignment 2, but you said like we will have 2 assignments.
Yeah, so this is the start of this assignment, and this is the end of assignment 1.
And for assignment,
this is, yeah.
Okay, I see. Now I see.
This is the end of assignment 1, and at the same time, start of assignment 2. So, yeah, maybe I should have made another row here, something like this. But yeah, I decided to say the row, and it created the confusion. Sorry about it. Yeah. So, and basically, you can also think of distribution of final projects. I guess it will be even the list of the topics probably will be available even earlier, but yeah, it will be more or less all this time. You will also be able to think and do something about it. Any more questions about logistics or grading?
Yes, I have one. There is in grading policy that if you are in top 20% public leaderboard, you get +7 to your score. Does it mean that, for example, if we have 25 students on this course, that only 5 can get the full score?
This is a good question. First of all, as I mentioned, it will be 5 and 5 here, not 7 and 3. So we discussed actually yesterday with the TAs, and it's actually maybe too much to say. Not much. These will be additional scores you get. So technically in Canvas, what you can have maximal score. But then if you can have some scores which actually go up above beyond this maximum score. So these
So the 30
you don't
is
complete some task. Yes, you don't complete some got the full scores on the final project, but you have this reserve.
The maximum is 37 points per assignment.
Yeah, if you get 25 here and 25 here twice, that will be 100% for the course. But
Yes.
you can get additional 10 points by being in the top. So 75, that's 100% of the points for the course. But you can get another 10 points, 10 credits by being in the top.
Okay.
Yeah.
Okay, I understand.
It's a very good question, and I think I will try to write it up. Anything more? If not, then just to remind you the schedule, we have a lecture and practice class, so 2 sessions a week, although you've seen in the agenda that in some weeks it will be a bit mixed because our invited speaker could not make it on Tuesday, so we had to rearrange the schedule and invite him on Thursday, and therefore we arranged the seminar or something like that. All right, so we are now done with the administrative part. I propose now to make a small 5-minute break, and then we go into some technical parts. All right. So let's start again. Yeah. A general term related to NLP is language technology. Language technology is about processing, developing systems, technical systems, which know something about natural language. Basically, information systems or computer programs which deal not with the formal languages, not programming languages, but with the naturally grown languages which we use now for communication. A fundamental difference between formal languages, which humans created and themselves for specific need in natural language, is that natural language is constantly changing system. It's not well-defined, and it has different levels, interpretation, meaning might depend on the context. This is not at all the true for foreign languages, yet designed to be simple and straightforwardly defined. So this is the reason why natural language processing is actually hard. The language itself is one of the most complex systems actually which exist, and the difficulty of dealing with natural language is that actually it exists somewhere in our brains. We use it to communicate, but yeah, it's quite hard to document, and because it's kind of a distributed system, which is always evolving. Under the umbrella of the term language technology, we have basically two different things. Sorry. We have two different terms. First is the natural language processing, or computational linguistics, and then it's speech technology. So NLP MCL refers to processing of written texts, while speech technology and technologies like ISR, automatic speech recognition, or automatic speech synthesis, it's basically such systems which deal with spoken language. In this course, we will mostly speak about natural language processing and some computational linguistics thing, because the field is so wide and the methods are so diverse that, yeah, I think to comprehensively cover speech technology, you probably need a separate class, separate course. Also, what is important is to understand the history of natural language processing development. So basically, natural language processing started somewhere in the 40s or 50s, where during the wartime there was a need to translate from German to English or from Russian to English. And for the military purposes, because, well, yeah, it was not quite just, there were practical needs to do this. And then there was a demand for research for on the systems, and some grants were allowed. Then the first wave of research in NLP, it basically used mathematical methods based on formal languages, and because somewhere in the 60s also there was a boom of development of programming languages, and well, you have languages here and languages there. you also have some semantics of programming language, semantics of natural language. Why wouldn't you use these things? And it seemed to be like a good idea. And in today's lectures, we will actually see that you can come a long way with this. But at some point, you will hit some barrier, and this field to this new paradigm based on statistical approaches and machine learning. This is where the field got its second basically wave of interest. New wave, which is based on reintroduction of neural models in NLP. Yeah.
Sometimes it is the variable when the sequence as an output. Without the body translates from one language to another, you don't know the length of the sentence for the first. For the sequence, similar way, you don't know.
All right. So guys, I ask you to try to mute while you listen, because sometimes I can hear what you say, so that might disturb basically some of the participants. All right. We will in this course mostly be based on the classical models. And actually, we have another course in Schooltech, which we usually teach. We will next time teach it in April and May, which will exclusively focus on neural models. And in this course, we provide some simple basic models, but also we touch on some neural approaches. But not as much as in another course. So I teach another course. We teach the last time in November, December, and next time is in April. Okay, so while the language processing is hard, this is mostly because of the presence of ambiguity on various levels, and the ambiguity is not there for programming language, for formal languages, but it's actually used in many ways in natural languages. And there is no easy way to cope with it. And you need actually to have, as a human, it might seem very easy to you to solve this problem, to get this sentence, and then to say, okay, this bunch of letters in this context, it corresponds to bank of the river, but the same for characters, given another bunch of characters around, it corresponds to another mental image of a bank. And at the same time, you have this bunch of characters and this bunch of characters, and they would refer to this same concept. So you see, this is a very complex relation between how we express some meanings and what they actually mean. And the fundamental problem here is that we cannot really measure what this means, even if we can somehow explain it in each other contexts. But even the notion of a word sense or a meaning of the sentence, well, it's not specified exactly. So we don't know exactly how many senses of the word bank there are, There are 3, 4, maybe some of you would count more. How many synonyms and what are there exactly the same meanings, or there are slight differences? This is the main fundamental problems where we have when we process languages. And the levels of linguistics analysis are also multiple. So here you can have some just person, and then the person can say something, and then what you have is you have some speech and sounds. So phonetics would deal with analysis of speeches and sounds. Then once we performed identification of words, then you would deal with morphological analysis. Then words would group into phrases and sentences, and this is syntactic level of analysis. But what the phrases and sentences mean, this is semantics. And then why people construct these phrases and sentences in a large text, this is what pragmatics tries to answer. And in this course, we will mostly focus on these 3 levels. And actually, in many practical NLP tasks, you will most often hit these 3 conceptions. So words, phrases, and maybe semantics of sentences and phrases. So yeah, these are 3 main levels which you need to know about well to do something on NLP already. Okay, any questions about this part, about the introduction to NLP? How many of you actually can say that you was doing something related to NLP, or you know something about it? Or you all more or less try to learn it from scratch, or you actually have some background in this field?
No idea in this field. I'm very new.
You know, okay, great. Anything else? Anybody? Okay, okay, yeah. So yeah, people write that. Yeah, okay. So great. Well, let me turn on light. Okay. Let them try to see some basics. Yeah, I know some of you might know about NLP, and you enroll for the course because you're interested in the topic. So for those of you who would try to design the course so that you can just show your skill, ace on the assignments, on the final project. You already do some research, you might even propose it as a part of your final project. And yeah, for those who are new, we try to explain the basics and show how to do the basics on seminars. All right, so let's speak of very basic notions for the rule-based NLP. And in the following lectures, we will be switching to more statistical approaches. But you will see that in doing many real practical projects, actually people do use rule-based approaches still. And the reason is that these are simple approaches which work, and to a certain degree, to a certain level of complexity of the task, they actually work very well. And also they work well as a post-processing step. You can have a very complex model which performs some neural-based transformer stuff, and then it doesn't exactly produce what you want, and there is no exactly the way to tune it a bit so that it produces something different. And then people, what in practice do, they wrap it with some layer of rules sometimes. So that's another reason why to learn about it. Okay, the rule-based approach is based on the natural formal languages. And language, the formal language is a collection of sentences of indefinite length, which are constructed through an alphabet of symbols. And in this paradigm, you have a grammar as a kind of a device which would generate all the sentences, enumerate all the sentences in the language. And also it can pass it so that if you give some sentence, it can say whether this sentence belongs to this language or it belongs to another language. These formal foundations of this idea were laid out by Noam Chomsky somewhere in the 60s, and since then it was used largely for developing various parsing systems for natural language, but also for programming languages. Formal grammar here is a kind of a tuple where you have four components. First is a set of non-terminals, and a set of terminals, and a set of production rules, which essentially can be formed from a union of terminals and terminals. You can take some combination of terminals and terminal symbols, and the rule basically say that this sequence of terminals and non-terminals can be rewritten as this sequence of terminals and non-terminals.
Professor, there is a question. What is terminal non-terminal means?
Terminal is a symbol which you basically want to obtain in the final sentence, and non-terminal is just some special symbol which your language is not belong to actually. It's just a symbol which you can use to do the production. So it's just a conception which, so once this production is completed, then you should have only a bunch of terminals.
Excuse me, Professor, could you please give an example on our usual natural language of terminal and non-terminal symbols? I didn't get it.
Yeah, I mean, I will use the chat. You can see it. Can you see the chat window
yes.
now? Okay, yeah. So in this case, the sentence, somebody wrote this sentence, and you want to produce two terminals, but we do not see the chat on your screen. Okay, but that. Okay, yes, I think that this is because I shared something. Let's say we have this sentence like is a finite set of non-terminals, and basically we have all these words which are terminals, but there could be some non-terminals which stay behind. Let's say I have set of non-terminals as a noun phrase. And this noun phrase can be denoted with like a variable and or finite set of non-terminals. We can just, you know, take this thing and say that's n. And this is a verb and a is a determiner. And then what we can say, hey, what I have usually in English, I have V and then D and then N, because you usually have in English like a verb and then some determiner and then a noun or noun phrase. Your English sentence may be as easy as that. And then you can say, hey, then I will develop N into, some more concrete terms. So this is how you should perceive it.
So V, D, and N are terminals in this case, and the finite set of non-terminals, these words that N consists of, are non-terminals. Did I get it correctly?
Yeah, but another way around. So non-terminals.
Okay. So the
T and N, and the terminals, the yes.
So
and also you have some start symbol, just like a root, which would be usually start of everything production. And from this start symbol, you try to derive some sentence using these production rules. And then if you are managing to derive this sentence using the set of production rules, then you can say that, yeah, this sentence actually belongs to this language on the basis of this grammar or a set of rules. Otherwise, yeah, this is not a sentence belonging to this language. It's like, I give you French sentence and you cannot like parse it. You cannot understand it. Why I cannot understand it? You cannot break it down into, what is verb, what is noun, what is determiner. It's just even if symbols are the same, then meaning of the sentence, the way the sentence is constructed is different. If I give you English sentence, your grammar, internal grammar, your set of production rules would break it down and try to make some semantics of it. And automaton is basically what is a device which takes this sentence as input and says what it belongs or not to a foreign language. So usually the overall structure looks like this. So you pick a grammar.
I'm sorry. Can you repeat the previous two slides because I didn't understand anything?
This one.
And the previous one too, because I didn't get the non-terminal and terminal concepts.
Okay, sure. What exactly you have a good trouble where you have 4 elements. 2 elements of is a set of terminals, the second is terminals. And then you have a production rules which allow you to form rules with a mixture of terminals and internals on left side and terminals and internals on the right side. These rules, they may say, if I have English sentence of form verb, determiner, and then noun phrase, then I can rewrite this thing. Okay, maybe I can try to use some share another screen. New share. Let me see. Yeah. Can you see something like this?
Yes.
Okay, so let's say I have like a verb and then determiner and then a noun. Let's say this is my grammar, and then I have like a start symbol. And start symbol can be, and this is English. So in English, you always have this verb, and the verb can be, let's say, is, it can be are, it can be go. And noun can be, let's say, man. It can be, in our case, what was it? Is yeah, a man or woman. And then determiner is something like this, something like A. And then what you can do, you can say, okay, we have this, and then we can generate this structure. And from this structure, we can generate like is a man. And this contain, and therefore, the things which are lowercase, the terminals. So you have this, all of these guys, the terminals, and all of these capitalized guys. And this is like a sentence which belongs to the language generated by this extremely simplistic grammar of English. Is it any clear? And the way, and if I pass to this machine something like are the woman, the automaton would accept it because there will be a way to parse the sentence using this grammar. So this is the grammar, and in this grammar we have a way so that we can apply a sequence of rules and go from the initial state to a state where all the symbols are terminals. This means that this automaton passed this sentence. This means that this sentence belongs to the grammar. On the other hand, if we have something like go to park, well, this sentence does not belong to this language, even though go is a verb, and then but to cannot be derived because determiner can be rewritten into to. So therefore, we cannot say that this sentence belongs to this language for this reason. Is it any clear?
Just clarification question. So like to here is a non-terminal, yes?
Another verb. Determiner. So this determiner would be yeah.
So the words that are possible but not in our like language, they are non-terminals.
Words which are possible.
So like the black words, they are terminals, and we can like construct the sentences according to the given rule, and it will be the sentence that is in our language. And if we dismiss the order or take the some another word, this word will be non-terminal, and the sentence won't be in our language like this.
Yes, exactly. If you have if you did not eliminate all non-terminals, then it's not in the language. Yes. If there is no way to eliminate all the terminals, you basically stuck in it's not derivable. Let me switch this screen. Okay, to try to make it. Like this, and then try to share back. Yeah. All right. So yeah, in this case, it will be not derived. There are a few types of grammars in this kind of. The most powerful is type 0 grammar, and overall we introduced overall we have entire hierarchy called Chomsky hierarchy. This type 0 grammar corresponds to the Turing machine, so recursive in neural languages, and this is most powerful one. The least expressive is context-sensitive grammar, and then there will be some limitations on the types of the rules which this grammar follow. So the rules should be either in this form. So you should have some internal here, and then or the rules should look like this. So this would correspond to linearly bounded automaton, and then even simpler grammar is a context-free grammar, which will be again some quadruple, but the rules will be just in this form. And the simplest one, so the context-free grammars are quite popular, and they were quite popular for constructing parsers for natural language, because they can almost describe phenomena for the natural languages structure. Like the sentence we described, you have some words, and then what you can have this grammar with production rules. So every sentence in English should be composed of noun phrase and verb phrase, and then noun phrase can be either just a single noun or a determiner followed by noun, or another noun phrase followed by prepositional phrase. And the verb phrase, again, this terminal can be rewritten as a verb followed by noun phrase, or a verb followed by noun phrase and preposition. And then at some point you get to actually lexical level. So a noun in this super simple language is either I, either elephant, or pajamas. Of course, this is not a realistic model of English because there are like 300,000 more words, but still, this is like a toy model of English. Then you have like a verb. Of course, we don't have only one verb in English, but in this case, we just list only one. And the same with the auxiliary verbs. The problem is that you have syntactic ambiguity in languages. So, you know, whether you shot an elephant in pajamas, so whether you was in pajamas or the elephant was in your pajamas, this might be not clear, and this would be modeled by different constituency trees. We call this tree, we will have an entire lecture on syntax, but the idea of constituency trees and constituency parsing is that you have different chunks of text, and then you group them together, and then you group them in larger groups according to some syntactic rules. So in this case, like a noun phrase is a combination of some noun which is modified by the determiner, but then you have larger noun phrase which contain basically more details about nouns. So here there's an elephant, and the elephant was in pajamas, and in this case, the guy was in the pajamas. All right. So the least complex type of grammars is a regular left-right linear grammar. In this grammar, the rules follow look like this. They either rewrite one non-terminal to terminal, or they rewrite one non-terminal to some terminal where another non-terminal fall on the right or on the left in terms of left-linear grammars. And these types of grammars, they generate regular languages. And regular languages defined like this. So the word language is regular, and then all symbols of regular languages also belong to this language. And then also you have basically three operations: union, composition, and cleaning star. In Russian, cleaning star called transitivное замыкание, for those who may be familiar with. And the idea is that, or if certain language fall and closed under these three operations, this will be regular language as well. So union would be correspond to this semantics of or, and composition is basically like concatenation in more common terms. And these regular languages, they can be defined or be equivalent for regular expressions. And this is actually what is used quite a lot for text processing, and this is why it's worth understanding a bit what is behind and what kind of expressivity you can obtain. Regular grammars so can be the exempt final set automata, and we've seen these different machines like Turing machine and then put down automaton, and they're basically very complex. And the automaton is, well, just a very simple thing. Is just a bunch of states with transitions between them, with a bunch of final states and starts and final states. And as you can see, you can actually implement these things extremely efficiently using some programming language, because it's just a kind of a graph where you have maybe labels on the transitions, on the edges, and maybe some information associated with the states, but otherwise, yeah, it's a really simple structure, which is nevertheless can allow you to do some text processing things. So here we see this correspondence. So the most powerful grammar, they correspond to the machine, but yeah, what is very often used in practice is at least for simple processing is FSAs. And for parsing is something like context-free or context-sensitive grammars. Here is just a small equivalence table which shows you, summarizes you what types of grammar correspond to what types of rules. So basically here, Turing equivalent or type 0, you just can rewrite everything to everything. Here, context-sensitive thing, you have some constraints, and yeah, the regular languages have languages like this, and this would correspond to regular language syntax, regular expression syntax, to the right linear grammar syntax. So as you can see that you can let's say you have just a terminal symbol E, and you can rewrite this symbol using this rule, or if you have like this EF, this is a concatenation of two regular languages which are defined, say by this and this. Okay, you can write a grammar which would correspond to this, and therefore you can write a final set automaton which would accept this regular expression For the clean star, so this would correspond to this epsilon. So to 0, the weight sequence, and so on and so forth. So you can combine these operations, so union or concatenation and clean star, to write very complex grammars, which would accept more and more complex languages. And using the property that regular grammars are closed under these operations, well, you will still be able to build some finite state automaton which will accept this language. So this is what is used in the property which is used to implement. Here is just one simple example of a regular expression, and this regular expression basically would take as input some sequence which contain 2 zeros in it. So this means that if whatever sequence of bits you have, if it has 2 zeros in it, it will belong to this language. And the grammar which would implement it, left right grammar, so that on the left we have some non-terminal, some terminal, and here we have non-terminal. It would look like this, just 2 rules. So here you have an original symbol, starting symbol, and then can rewrite it and like this, and this grammar would accept sentences like this using this automaton. As you can see, if you want to write a program which would recognize all sentences in the language, well, this is just as simple as building this graph with 3 states and a few groups. And obviously the reason why these regular expressions and regular languages are so used is this the computational efficiency, that you can apply it and use it on a very large amounts of data. You can compile them in some kind of machine instructions and get it might find something extremely efficient. Speaking of these, by the way, so there is any questions so far? Is this any clear? Many of you already used regular expressions and things like that, or this is like more like concept?
Where can we get this more in details? I mean, I'm totally sure that I will not get everything right away from the lecture. Yes.
We will have, so I'm recording the lecture, and hopefully recording will be available afterwards. So we do it for the first time, but normally I will upload the video if everything goes smoothly, and the slides as well, they will be available. Besides, I provide textbooks, links to the textbook.
Yeah, there is someone writes, I lost somewhere after terminals. So basically it's also for me too, because I mean, I get some knowledge from it with the general context, but in details, I'm not sure, especially regular expressions I hear for the first time. I mean, not for the first time, but in this.
Yeah, that's, I can try to repeat again, because it seems that there was some confusion about notions of terminals and terminals. Let me just try to maybe return to this example. Think of English. And in English, we have certain structure of sentence. I like my dog. So first we have some noun, then the verb, and maybe then some other noun. S is just like a variable. So this non-terminal thing is like a variable, which would denote sentence. And then these production rules, they say, well, you can split this variable, which has, so every variable in this set of non-terminals, it has specific semantics, it has specific meaning. We have a variable for sentence, we have a variable for noun, we have a variable for verb, we have a variable for determiner, some other parts of speeches, something like this. Or prepositional phrase, phrase which contain, this preposition in my pajamas. In my pajamas, so this PP is like a variable which can be developed in English in my pajamas, or in my jeans, or in my juice. But it will be still PP because PP would denote a non-terminal for all of the things. So is it any more clear? At least the notion of what this means, what it's used for, or not quite.
I didn't get what's the purpose of grouping the non-terminals like noun, verb, determinal, like in this PP and PVP. What's
to manage the complexity of language, basically. In language, okay, this is an abstraction. This is an abstraction, and the language is not just a bunch of random bytes. So people would describe the language according to certain theory, like the fact that it has different parts of speeches, for instance. Verb would be the part of speech, one of the part of speech, which would group it. I'm not sure did I answer your question, but given that you agree with the fact that in English there is certain order of words in a sentence, I think it should be more or less okay to agree that you have different part of speeches, and therefore you might want to group them. But does this make any sense?
Oh, well, I partially understood that we want to have some more general constructions in the language, but still this list can be as extensive as just the number of the primitive non-terminals. So like this is counterintuitive for me.
It can be, but then you learn yourself language like English in school. Do you remember how they try to teach you it? I mean, they did not just give you lists of words. They also try to teach you some grammar, right? So how to build sentences.
Okay.
Write sentence in English. So this is, then there is certain structure of the sentence. You should always have a verb in the sentence. Usually, in the majority of the cases, if you have the verb, then noun usually falls after the verb or something like this. This is an abstraction, and I agree that often people try to argue that this is not the right abstraction, or this is not the right way to conceptualize language. But this is a common approach which proven to be useful in some applications. So I think empirically this makes sense.
Yeah, it's clear. Thank you.
But it's really, this is exactly the problem I mentioned, why NLP and designing information systems which know some kind of language is hard. It's not clear how to measure all of these NPs and VPs in our brain. When we speak, we just speak, right? We don't speak like I draw some dependency tree first or consistency tree, and then I make an inference and stuff. No, we don't do like this, but it might be useful in some applications to, let's say, to perform information extraction. Let's say Obama met with Merkel in Berlin. It could be sentence like this, and then there could be like entity like Obama and then Merkel, and then they can be verb, and then if met may correspond to the fact that there was a meeting, and then there is a place Berlin, and these all they are pretty concrete, discrete categories like location or person or the verb. So you can say that Obama and Matt and Believe and In, they are just tokens, but often it's useful to separate and to introduce these groups.
Okay.
More clarification questions on this? Don't feel free to ask me, because I'm happy to clarify something if I can. Okay, if not, then grammar is a function of. I have a question on the chat. Okay, grammar is a function of noun, verb, pronoun, etc. No, grammar is not a function of noun, verb, pronoun. It's more like something which generates language. And noun and pronoun and determiner, they are parts of speeches. And they are used as a variables, as a beans to hold different words. In one bean we have all nouns, in another bean we have all verbs, in another bean we have all adjectives, and then we can combine them together through this combination. Yeah. Okay. So if there is no more questions, then I'll proceed, but feel free to ask later. Okay, so regarding the regular expression, so the useful thing about it is that if you have a sentence like this, input thing sentence like this, you can ask this grammar whether this sentence belong or not to this language using this very simple machine. So if you say something like 1111, this machine will be able to say, sorry, I don't understand you, this is not in this language. So, and you can call it okay. The proper lemma is something else related to regular languages, and it says that it's formulated like this. So if A is a regular language, then there is a number P such that if S is any string in this language with like at least this P, then this sentence may be divided into pieces so that these preconditions are met. These preconditions are like this. So first condition is meaning that you divide the string into 3 parts, and then the middle part you can pump. So for any positive integer, this pumped version of the input string will also belong to the language. These conditions, they basically just say that second condition says that this guy is not 0 length, so it's not like a trivial pumping of nothing would result in nothing, so that would not be a good thing to do. And this means that this condition asks for this to be at least of length p. And let's take a look at some example of using this lemma to prove that the language is regular. So you can have this very simple language, which is like this. If W begins with 1 and ends with 0, that, with anything in between, then this will be a sentence belonging to this language. And then let's assume that this P is free. And then we take some string, which is longer than this P, and then we break it down. So we break it down like this. So we say X is 1, Y is this, 0, 1, and then Z is what remains. So basically we take this first character, these two characters, and then we show that, okay, we can have, we can pump this Y, but the string still has this property with starting from 1 and ending with 0. Therefore, it is a sentence which belongs to this language, and therefore we have proven that the language is regular. And here is another example showing that.
Sorry, I have a question on the previous lemma.
Yeah, sure.
Just why this result is interesting, because we just have some string, we split it in such a way that the very first letter and the very last letter are not affected by pumping the middle. And the rule, according to the we have already satisfied the rule by splitting the string in such a way. And what's the idea of the lemma then?
Maybe it will be clear if I show another example of a language which is not regular, because the idea is that you often cannot do this splitting. So if you cannot split, then it's not regular. Let me try to show the example, and maybe if it's not clear still, I will try to clarify.
Okay.
Okay, so this is an example of another language where we have n being an integer, and then 0 and 1, this is the center. So we have some long sequence of zeros and then long sequence of ones. Then we try to perform all the splits and show that there is no splits which can be pumped, so that we have still this property holding. So let's P beside length, and let's assume that we have this string to be like this. So 0 P minus 1, 0 P minus 1 in the power by P minus 1. And then really the goal of using this lemma is to try to split this given string into several pieces and show that we are able to pump this middle part if we show that such kind of split is not possible, we exhausted all possible splits, then we can show that the language is not regular. So in this case, we can have just strings like this. So we have if y contains only zeros, then it will be valid lemma. then if y would, so the part we want to pump contain only once, then it would again violate lemma, because n, the number of words in the prefix, in the same way as in the first case, will not be equivalent to the number of zeros, will not be equivalent to the number of ones. So fixing y on this guy or this guy wouldn't work. And the only choice in this case would be to select y to be at the same time 0 and 1. But it also doesn't work, because it would produce the same number of 0 and 1s in the language. But the structure of the strings will be different, because they would be alternating. They will be 0, 1, and then 0, 1, and then 0, 1. And what we want first a sequence of zeros and then sequence of ones. So because there is no other way to split the string, then we show that this is not real language. And the only interest why I show you it is because the English language in its very simple form can be also described as like this. So you have something like noun, usually followed by verb, but this construction can be nested. Let's say you can have the cat died. So die is a verb, cat is noun. But then you can have this noun phrase, the cat, the dog chased, died. So in this case, okay, this is noun, but this is a verb, and this is a kind of modified noun. You can essentially continue the loop: the cat, the dog, the rat, bit chased, died, and so on and so forth. So basically, you will have these several nouns first: the cat, the dog, the rat, the elephant, admitted, bit chased, died. This is a kind of a classical example. You usually don't observe that often in this ridiculous form, but you can observe this in this form, and this is just English, and this might show you that well, like kind of the first indication why such a simple approaches like rule-based or regular languages would not cover completely natural language processing in its entirety of applications. Yet it can be still useful for some cases. Okay, so after this example, is this requires some more clarifications or it became clear?
One question, but like in practice, we don't. I don't know actually, but do we? I think that we don't have like this generation rule of the noun and times and verb and times. So how this lemma should be applied? So we like should brute force all the possible language variant, or how? So the short question: how does this lemma should be applied in real cases?
In real cases, it's more like to show you why certain machinery would not be adequate to perform processing of all possible English sentences. So basically, you have English language, and then let's say you want to design a semantic parser of English using regular expressions and RE module in Python. Well, probably you will fail just from this theoretical standpoint, because English language is a construction which cannot be modeled completely and accurately with these formalisms. So this is to show you that you can have some I don't know, controlled language. You process some, medical texts, and then, or you process some, I don't know, sequences, and then you try to analyze what kind of data you apply, and you realize, hey, the language, the sub-language, the domain I try to apply looks like a regular language. Good, I can easily apply this kind of grammars. It will be fast. It will be no problem. If you have another data, like an open domain data, English data, then probably you should not use too simple tool to solve too complex problem. This is basically the way to apply.
But like without this generation rule, how can we just check that the given like set of sentences is under the constraints of this lemma? Like I can reformulate the question. Sorry. Like we don't have this rule like noun and verb, but we have an assumption that some sentences in our text can form this regular language. So we should.
Yeah, this is
which rule we should check.
This is
generation rule.
Sure, it all depends if you also can conceptualize using some symbols. If you have the data where you don't have this, or you cannot construct this kind of rules, or you cannot borrow these rules from some source. Let's say you process French language and you have some classical grammars of French, which are put in the computational form by some linguists. And then you can study, let's say, ancient French texts on the basis of these grammars, and then you can make some maybe derivations or judgments about complexity of the language. For instance, using this lemma, given some grammar. Of course, if you don't have grammar, yeah, that would be more problematic. This is, I would say, not as practical thing as we usually do to apply pump and lemma to check something, but it's more to show you the possible link between formal languages and natural languages, and how even simple check, simple example can show that natural languages are much more expressive than regular languages. And this is not a good idea to assume that you can solve everything with regular expression. So basically the reason why I put this into here is more this rather than to say that you should go after this session and check everything with pump and lemma. So it's, yeah, should be aware of it, but as you say, if you are not given concrete rules, it would be more hard to apply.
Okay, thank you.
Yeah, all right. So let me maybe finalize this part quickly. Formal languages, natural language, very different. By design programming languages, deterministic, context free in the most cases. That's why you can efficiently parse them. No ambiguities, semantics clearly defined. Not at all the case for natural languages. Semantic is not clearly defined. Ambiguities are everywhere. If you would estimate computational complexity, it's somewhere in between type 1 and type 2 grammars. So, however, there are some advantages of dealing with rules. They're computationally very effective, as you've seen. Have this small automaton and it can do something real. It can check whether this might present or not in a sequence of characters, sequence of tokens, which is tags. High precision can be obtained if you know what you do, if your system of the rules is adequate. But again, returning to the question, last question, well, when you get this bunch of rules, you don't usually have them beforehand. You need to write them for this concrete problem, and this is not extremely flexible and good approach very often. Another fundamental problem with this kind of programming language inspired NLP is that it doesn't really take into account statistical information, and almost everything in language is distributed according to some zip flow, according to some power law distribution. And these rules, they basically completely ignore this fact. So they assume that derivation, all the derivations are equivalently possible, which is not at all the case. There are a few of words which are extremely rich, extremely frequent, and there is a very long tail of words in phrases and constructions and syntactic rules and things like that, which are not popular, are not so used. And this fundamental property of language should be taken into account in almost every NLP system to make it work. And this is not really taken into account in the rules. Okay, so at this point, I propose to make another small break, and then we will have our final session and final part of the presentation on more concrete morphological All right. So let's start. Again. Right, so I hope you can see my screen again. Yeah, so you first task which we will speak about is morphology. Morphology is about processing individual words and trying to understand what are these at the lexical level. Because morphology works very regularly, so if you have an English noun, usually in the plural form, you will have to add s or es in it to get it. If you want to get supreme form, you add est or ist. And the same is for German, like adding some characters, postfixes in the end of the string would modify its morphological function, would modify the inflection. And essentially, the task of morphological analysis is the task of getting the words and assigning a bunch of texts to this word, which contain lemma. Lemma is the basic form of this word. If you have runs, then what you want to get its basic form run, so singular form. And then you want to get it part of speech tag, whether it's a verb or a noun, and then depending on part of speech tags, the set of other categories might be different. So if it's a noun, you have just a plural or a singular. If it's a verb, then you have kind of a form tense in which you observe it, whether it's present form or it's past partial and things like that. It's the same idea basically generalizes over other languages. So you usually have different names for these syntactic categories, but you can think of it like from the machine learning perspective, like you have as input a token, a verb in some form, like you observe it in text, like, you know, utilized, and then you need to say what is it as in the basic form, like utilize. and then you need to say that in this form it was past participle.
Sorry, are you showing slides right now? Because we can see them.
See new share like this. Okay, can you see now?
Yes.
Okay, yeah, good, thank you. So this we're just explaining this slide with the examples, like you have run as input, and then a lemma which is run here runs, and then you have different categories of this input. It can be verb, it can be noun, and if it's a noun, it can be plural in this case, or if it's a verb, it can be a verb in the present form. And this kind of thing with generalized finite languages for German would be the same. You have a lemma boot for boot, but for verbs as well, you have different categories which characterize this particular occurrence of this particular verb. And this is the morphological analysis all about. The classic approach to this kind of morphological analysis is based on finite set transducers. And this is like extended finite set automaton, with the difference being two additional components. So this similarly to FSA, you have a set of states, you have alphabet, and so the final states, but you also transition between the states, but you also have output alphabet, and output alphabet would be used in this transition function. So FST can be seen as this finite state automaton with two tapes. It reads some sequence, reads some sentence from a language, but it also generates a sentence while it does it. And this out sentence is using this alphabet, not the alphabet. So this kind of FST, it said that it accepts regular relations, not irregular expressions. And the regular relation would be defined like this. So you have these two alphabets, and this is like a tuple would be with a symbol from one and another would be some relation. The definition of regular relations is pretty much the same as those of regular expressions. So you have an empty set, which is regular relations, and then you have these alphabets and the concatenation between composition between symbols from these is also regular relations, and they are basically closed as well as regular expressions under union and concatenation and clean enclosure. What is also used is a composition, projection, inversion of these relations. So the composition is then you have one FST, such as this one, and then another one, and then you can compose them, and then you will have another FST, which would perform some complex function. So this notation usually would mean that this is the input symbol and this is the output symbol. In this case, you have the first state, and then this automaton would accept some sentence which starts with A, and then it can iterate through some sentence sequence of B's. And while doing it, it would output X in this case and Y in this case. So this automaton would takes as input X, and then it would generate nothing, and then it would take as input Y, and it would generate Z. So therefore, you can see that the output of this guy is input for this guy, and this would make this composition possible and practical to basically make some abstraction of this processing. Yes, sorry guys for not showing the slides at the beginning. Yeah, I hope now it's working fine. Yeah, so basically the output of one automaton, or for instance transducer, can be an input for another one, and therefore if you compose them, you will obtain this result. So you can, as if you read sequence A, BB, then you will output nothing, and then you will output several, you output two Z's, right? Whereas if you parse sentence A, BB for this guy, it would output X, YY, yeah, which will be different from the composed one. Okay. This is just another example which might make it a little bit more clear why we would bother with these automatons and transducers. This is an example of morphological, some simple morphological analyzer of three German words and their inflections. So you have this word and this word and this word, and as you can see, they are morphemes, their roots, they're different, but then you have fairly irregular structure of the inflections. So if it's ends with en, well, it would mean it's a third plural or first plural. And if it's these words would end with at, it would mean that this is a third genre singular. And if it ends with est, then this is second genre singular. This is how you would actually generate these tags, which I showed you in the beginning, right? So you would read this sequence, and then once you would observe this ending, you would generate some of these tags. This is a simple way to do it. But FST is also non-deterministic because you have these epsilon transitions, and you need to handle this determinism somehow. We sometimes don't. What this means practically, we sometimes don't know the path which we have to take, and we need to keep track of several paths. And then we might, according to some heuristic or some machine learning model, to select some path which or result which better fits a given context. This is one of the examples of such kind of parsing. So you have this input word runs, and this is a string. or a sequence which you process, and then you have this transducer with these guys being inputs and these guys being outputs. And what happens is that you have the second tape, which is analyzed, lemmatized version, and with the version with this morphological text. Well, for this one, what you do, you read this first character, and then you read the second character, and then you read the third character, and so far there is no actually ambiguity. You just have one option to proceed in this through the states or the bottom. And then what happens is actually you have to make another tape or make another branch of this morphological analysis, because what happens is that you have runs can be a plural in terms of noun, as a noun, or it can be basically a third form of a verb. And this is if without knowledge of context you cannot tell one from another. This is the reason why you then would generate several outputs, and this was what you will end up having in the end. You reach the output, and then you obtained two options. This is something which you will also see on the seminar, where you will use some real morphological analysis, some analyzers, for instance, for Russian language, like Morphology 2. The Morphology would use some dictionary-based morphological analysis similar to this one, although it might use slightly different data structures, and it would yield you a list of options. So a list of various parsing of different words. So this is exactly the reason why it would produce you the list. It cannot exactly, there are several variants of morphological analysis which correspond to the given input, and without using more powerful and computationally also more heavy tools, you cannot really tell one from another. In practice, in many applications, you don't really need to disambiguate this carefully, but in some applications you need, and in those which you need, you do it, and you pay additional computational cost for doing it. Yeah. Okay, so I think that this block about FSTs, I just would like to understand if there is any questions about it, or it's more or less clear how and why we would do it. So, if there are no questions, then I will proceed, but you can ask me later about this. Okay, so no questions about it.
Well, actually, not as for me, that not none questions, but there are too many questions, because it's a bit faster for me as you read, because like just a lot of unknown terms, and like I'm a bit lost.
I think it's
Agreed.
It's fine. We will try to also provide recordings and on the seminars to what you can do. You can gather maybe some additional clarification questions, and we can try to see what things were not clear. and also try to maybe read the chapter if in terms of conceptually it's not clear. So I provided some names of numbers of the chapters from Jurowski Martin book.
Yeah, I'll try it at home, but like I'm reflect on the current. Like.
Yeah. Okay. Good. So this is good. I would not be happy if you just already know everything from what I try to say, because that would not be useful to make lectures about it. Okay.
Alexander,
Yes.
how could you say how seminars, how well connected seminars will be to the lectures? Because maybe it would be easier for us to understand the lecture material on the seminars if the seminars will be based on lectures like this.
We try to align one with another, but of course the seminars will be much more practical oriented. For instance, on seminars, you will try to run and maybe look at implementations of some concrete morphological analyzers. Let's say for Russian, you have with this PyMorphy morphological analyzer. And what it does more or less this. You can get some word to this analyzer, and it would output different morphological tags which correspond to this word. Now, maybe there will be some additional parts as well. On the seminars, let's say for the rule-based approach, we will try to look at how you can do information extraction using rule-based things. Something like the Yandex Tomita parser. Let's say you can parse CVs and extract different parts of it. But so it's somehow connected, but it's not slide by slide connected. Okay. All right, then the Zoom is supposed to stop, I think at 7. I'm not sure whether it's strict or not, but I will try to finish in time. If not, we can maybe stop, continue in the beginning of next lecture. So one of the abstractions which people introduced to enhance the system a bit is to introduce 2 layers of morphological analysis. So first is from the surface form to morphemes, and the second from morphemes to morphological analysis. So the surface form is in this language is what you observe, like the words which you can directly observe. This is what in these levels of linguistic analysis usually called a surface form. And all other forms, they are kind of layers of conceptualization, and morphemes is morpheme analysis is one of them, like kind of an abstraction layer which help you to break down the problem and solve it more efficiently. It's like with the programming languages, like another layer of abstraction always solves all the tasks. There is no problem, you can solve it, edit another layer of abstraction. So this is the same here. Like what happens is that you have this lexical level, surface level, and then you have intermediate level, which corresponds to morphemes. Like maybe you remember from the secondary school, you done this. Okay, you are given a word, and then you need to get the root, you get the prefix, you get the other parts of the word, and this is exactly it. So you got a word, and then you need to break down the word into different parts, meaningful parts, and then another analyzer would take care of taking these as input and then producing some morphological analysis, basically saying that this is a noun, this is a plural of a noun, but not on the basis of directly the surface, but on the basis of intermediate output of some other transducer. And the reason why this actually people were doing this is because the complexity of this transducer might be extremely large for some realistic language processing tasks. So think of English having 100,000 of quite frequent, I mean, commonly used words. You think of a graph which corresponds to 100,000 words. It will be like enormous, like a gigantic graph, and this is why they wanted to compress it through these two layers. So this basically would mean that, yeah, you would perform this analysis on the basis of first lexical level, then intermediate level, and then a composition of these FSTs, like the function and intersection of these FSTs would be the tool to build a final set transducer, which would eventually process and perform this morphological analysis. All right, so these FSTs, so they basically can be used for performing morphological analysis, morphological synthesis, and the kind of data structures for spelling analysis, but also they have been used for all other tasks. But I would say now it's less popular to use these complex tools for other tasks, but for morphological analysis, it's still maybe a valid tool to use. Right. So this was one way to deal with morphology. There is two more ways, and they are basically using simpler approach, which in terms of computational complexity, because if you think about it, these FSTs, they are graphs which would be quite large for a large number of words. You would need to store them. They take a lot of memory, and there will be a lot of redundancy in these graphs by construction. So this is why tries are often used for simpler and quicker morphological analysis. So tries or prefix trees, they are data structures which look like this. So given some set of input strings, what you do, you construct a tree so that every node of this tree corresponds to one character, and common prefixes. Basically, the common beginnings of these strings would be grouped in this tree. So if you have, if you want to store these 4 names, for German names in a tree, if you want to construct a data structure, then one can construct such kind of a prefix tree, which would contain 17 nodes and 16 characters and 16 edges. And it will be more efficient than storing individually all of these, let's say in a hash table, because then what you will save, well, in this case, not that much because you have only 4 strings, but already something because you have some common prefixes. But think about it, like you have 100,000, 300,000 of words, and a lot of words starts from the very same prefixes. So you will have a lot of common paths, and the amount of storage you need is much less. All right. Another way to compress and to reduce the number of bytes you want to spend storing your list of words is Patricia try or Redis try. This data structure is almost the same, but it performs some merging of sequences, sequences of characters. The sequences of characters which have no branching. So we have this Juta, and then, well, we can just have one node for Juta. We don't need all of these 5 nodes, which each of them, it would take additional memory. It would allocate some data structure, which would have, I don't know, like a structure with the pointer to the root, pointer to the next node, something like this. We can have just one node, and the same thing here. So this would reduce the number of nodes from 17 to 7, and obviously the number of edges as well. That would be Patricia try. And to perform a search in such kind of data structure, well, you given a string, and then you basically eat the characters from the beginning of your string, and then you follow the tree. If you have like a Maria as input, well, and root, then you read the first characters. You see, okay, I have Ma here, and then what is next is R, and then you given this EA, and then end of the sequence symbol, and then you end up somewhere in the leaf of this data structure. And if you ended up in the leaf, this means you have exact match. This means that you have this string contained in the view source. If you ended up somewhere like here and you're stuck, this means that this input string is not contained in your dictionary. And it would mean that, like, you have a hash table and then you perform the lookup, like you ask the key in the hash table, and there was no such a key, you know. And that would correspond to this, but the difference is that hash table doesn't allow a partial match. Let's say we have a Julia, but for Julia we actually have a match of first 2 characters, and the nice property of this Patricia tries is that you can still use some information, something about this partial match to do something, to classify the word, for instance. So, how to insert new strings into this data structure? Well, first you need to find the place where you want to insert it. So you get a new string, like Marielle in this case, and then you go until you're stuck. So until you cannot proceed further. So in this case, the first node would fit, but then Noella would not correspond neither to this LT, neither to R. So in this case, what happens is that you can create basically a new node with the reminder of this input string, and the insertion will be completed. In some other cases, like this one, what you might need to do, you might need to split original string and relocate the reminder to find some common prefix between the input string, like here, Johannes, and Utah. So basically the common character, because Utah and Johannes is J, and you would put J here as a common one, and then you would yeah, create two new nodes, and this node will be deleted. Yeah, any questions until this point? So far so good? Right, so
Yeah, it's okay.
So this is pretty standard structure, and what we gain through this Patricia trick is the storage. So if we have length is capital M, and then number of strings stored in the try being n, that's alphabet n, then the insertion, deletion, search operations theoretically will not be changed. So they will be proportional to essentially the length of the string you want input, and the set of alphabet, because the branching of this tree will be dramatically different for different alphabets. The more the alphabet, the more branches you have, the more complexity, the more branches you need to check. But in this case, you gain storage, which is actually quite important if, let's say, you want to integrate it into your mobile phone. Let's say you make a spell checker for an iPhone, and you cannot just allocate a huge hash table or something like this. You want something really compact, then maybe this data structure will fit better. And another feature of this Patricia tries, which can be used, is to associate some meta information with the nodes, such as in this case, gender of the first names. So you have this Marcus and Maria and Yuta. So Yuta is a female name, and Marcus is a masculine, is a male. Maria can be both female and male, depending on culture, but then what you can do, you can actually classify a given input string into male or female name using this trees. So you can, if you provide directly Marcus, and you here, well, you know that Marcus is a male and Yuda is a female. Interesting thing starts when you actually look at these intermediate nodes, because they also contain some aggregated counts of the classes. So for, and they basically just sum up all the class categories from the leaves. And the same happens here. So this is basically a sum of M2 and M1 and F1. The same happens here. So, and this gives you distribution of classes overall in the data. Why this is useful? Because you can perform categorization of incomplete sequences as well. Let's say you have Martin now. You never observed it during training, or let's call it training and construction of this tree. And then you go like here, and then it's not Marcos, it's not Maria, but the dominant class in this node is male. So you can assume that Martin is also a male because it's more often to have male classes for the string started with Mar, something like this. Okay, so far so good. If yes, then it's another example of using this idea basically to perform this morphological analysis and lemmatization using this idea of attaching something to the nodes, some meta information to the nodes of Patricia Tri. Well, you can attach not only information about gender, but you can also attach some rules which would say what to do with a given input string. If you have a house, and so this is a bunch of German words in different inflections. And if you want to get a lemma, we can write the rules like this. If you don't need to do anything, it's 0. If you need to delete 2 characters from the end, it's 2. So the number will always mean how many things you need to delete from the end, and then this would mean what you need to add to get the basic form. So in this case, like house is a basic form, and this is a plural. So what you need to do here is to delete these 2 characters, and then you will get house again. What need to do about this guy? Well, this umlaut spoils everything, so we need to delete all the 5 symbols and then add aus here. So, and then again we'll get house. How about mouse is a basic lemma. Don't need to do anything about it. With mouse, again, delete 4 characters because this umlaut, and then add aus. The same thing here. So this is just kind of a notation for the writing rules. And we can write now this Patricia Tri in the same way, but using labels which correspond to these rules. The only difference will be that we actually have to write this from the end. So we will write words from the end to the beginning, not from the beginning to the end, like we done with the example of genders. And then you will see that what happening is that yeah, you have this input word bow. You don't need to do anything about it, and then you have something like, so you also read from the end. You read es, so s, es, and then you need to delete these last 2 characters to get a normal form. So this is the notation, and then the point is that you can put some unknown word here and then still get it lemmatized. So because of this regularity of the flexions, you don't really care about the beginning of the word, whether it's Hochhaus or Spaß or Intervals. Doesn't matter. What matters is that these last few words, letters which behave irregularly, and if you pass this Unterpause here, okay, S and then UA, and then like B, and then this means you need to remove this guy this last character, and then you will get the label, Unterbau. The beauty of it is that you never put in these three Unterbaus, but you actually manage to perform its morphological analysis. And another trick which can be used in conjunction with this is making the tree more compact, storing even less, to store even less memory. To do so, you can actually just throw away those nodes which are trivial, which correspond to the dominant class of the root node. So the idea is like this: if I get this bow, and the bow has class 0. Why would I store this node? Because if I never observe bow, I would end up assigning 0 class anyways, because it's most frequent class. So I would remove this guy. The same here. Why remove this node in this node and this node? Well, because if I never absorb this, I would assign 0 anyways. And this is just one pruning trick which can allow you again to manage efficiently the stores. So in the end, for Patricia tries, you can use it for storing of dictionary in a very compact form, much more compact than hash table. You will see on the seminar some concrete example of using hash table versus, well, not compact Patricia trie, but some even more advanced trie structure called Marisa trie. And the difference is very big. So if you store some list of words, or if you store some other lexical items, let's say the distribution of thesaurus, like a list of lexical relations, something like this, it's very good. And you can use it for base form deduction and morphological specification, and some other simple morphological tasks. Yeah, yeah, this is what I wanted to say about tries. We have any questions at this point? If not, I can try to proceed. Okay. So the last data structure to consider is called DAFC. And DAFC stands for Undirected Acyclic Word Graph. It's even simpler data structure, and it's built on the character level. And the crucial difference between DAFC and Patricia tries is that it collapses at the same time suffixes and prefixes, which makes it even more efficient in terms of space. But this very feature does not allow us then to store any additional information about classes, because the uniqueness of the path is lost to this point. And the simple example of this structure for storing of these 4 words is look like this. So you have these characters, and then the types of pointers can be 2, and the next pointer is like alternating path and can give you alternative path, and the C child pointer means that you need to proceed from this node to this node. So this is what, and this would be denoting the end. This means if you reach this guy, this means that you managed to read entire word. All right, and Jurspot. So this is like some sausage kind of bread. This will be corresponding to path like this. And then if you want to search something, you want to start and then to kick out words from the beginning and trying to follow the paths. If you reach a node with n, so the next pointer you can try to select among these, and then you can proceed. And if there is no way path, this means that your string is not in Dask. You don't have it there. For the construction of this data structure, you need first to put symbol by symbol, create for every symbol create some node, and then you can create these alternative branches, and that doesn't look actually very efficient, right? Because what happening is that you create for every chart its own node. It's actually the same as stored in a list or in a hash table. What makes this structure efficient is the procedure of merging prefixes and then merging suffixes, so that you try to find common suffix here, and if these coincide, you just create this you delete some node from here, and then you reallocate the pointer until the position that they don't match, which is here, and the same happening for the prefix, basically. Yeah. So this is a simple data structure, and which can be used to store extremely efficiently word lists or some dictionaries, but it cannot be used for this kind of association of classes, because you can have multiple paths through this, and this from the input to the output, and one AND node can correspond to several input strings, which doesn't make it therefore possible to allocate, associate uniquely one input string with one particular output. Yeah, but this is still can be used for Scrabble or some other more practical use cases. Yeah. Yes, sorry for getting until the point, but yes. Okay, but this basically completes our main part of our talk today, and we have hopefully some 5 more minutes until the end of the lecture. But what I basically also have, I have a few slides on a few more fancy future directions on morphological analysis, which may capture your attention and maybe which might motivate you to do something about morphology. And this is something what actually people do quite recently. This is a paper from Top Conference on NLP, like 2020 ACL, from a group of Schutze from Munich. And this is they develop a model for developing actually morphological, the growth of morphologies and families. So let's say they took the politics braid, and then they analyzed that you have this Trump, and then the Trump starts to get more and more inflections. So this is what called paradigm. So the set of all of these strings, it's called paradigm. And what was observed that after election of Trump, after then obviously he got a lot of this paradigm started to grow, and they try to predict this on the basis of sociological and other factors. Another task which is common as morphological reflection, there was actually several shared tasks on this, and the idea is that you have the lemma as input, and then the task is to predict these tags. It's a kind of a machine learning setup, and people reach up to 96% accuracy, but not on low resource settings. Lots of training data, good language like English. You can solve this task well, but maybe not in Belarusian or some language where not as many training data available. Another task which is common and people do it is paradigm completion. So you have this paradigm again, so a set of all various versions of the word in different flexions, and you gotta fill the gaps here. And again, this is kind of machine learning setup. And of course, not all the words are regularly spelled. The language has lots of exceptions and rules and stuff. So this is not necessarily a straightforward task. Another way is like paradigm discovery. So you have a word, and then the paradigm again is a set of all various flexions. And if you have a new word, you know, like in whatever it may be, like a selfie, or Google. Before we had like just Google, but then to Google, and then Googling and whatever not. But before it was just the name of a company, and then new words emerged in the language, and idea that you might want to discover these words automatically, not wait until somebody in the dictionary will write it for you. You might want to do it from scratch. Also, another task is to try to learn how to use context to perform proper morphological analysis. The models we see so far, they just completely contextless, so they don't use this context, but context might, of course, be very important to solve the task. And another thing is to use high resource languages like English, Spanish, to inform languages with less data, less information, to do this morphological analysis. The reason why this became popular and possible is that around 2015, a new project called Unimorph started, and this project is basically creating morphological annotations for many different languages, like hundreds of different languages, in the similar form. And what this means is that then you can use this common schema of annotation to learn from low resource languages to high resource languages. And people performed different tasks based on this data set. And yeah, for instance, 2018 task, it performed morphological analysis for 52 different languages, which I find extremely fascinating. And another thing probably you need to know is that, okay, the models we see today, they are very simple, they are basic, classical, you can get some results with them. Now you have also neural approaches, such as those based on sec-to-sec models. And you can also look at these two models like Aharoni-Goldberg and Makarov-Clementina. They're also based on more like neural approaches, and they usually perform better because they can, for instance, tackle with the context and tackle better with unseen words and things like that. So yeah, these approaches yield state of the art. Okay, so this is, I think, it. I think this is time for us. If you have any questions, I will be still happy to answer. If not, we'll see you on the seminar. Okay, I have a question. Where can I read about morphology? Yes, we have, I think, a reference in the book. Yes, in the Juravsky you can read. There is a couple of chapters about morphological analysis. Let me open. Maybe. Yes. Okay. I'm not sure that I will be able to post the slides before the lecture, because I will try to post the slide before the lecture, yes, but just some minutes before, because I might change something. Okay, so thank you very much for the questions, and I will try to post some links and slides just after right now. Okay, I will be available in the comments. Thank you for coming. Bye.